If you're seeing this video for the first time and it's prior to your having studied the content, the textual content of chapter 6.2, then this represents a preview of the important things that you will see in this chapter. If you're seeing this video after you've looked at all the content, studied it in chapter 6.2, then this represents a review of the more important things that you should take away from your studies. In this chapter, we introduce a quantity called the gravitational potential energy. We symbolize all potential energies, and there will be a second kind of potential energy later in this preview or review, as U. It's equal to the weight of the object, mg, times its elevation. It's an energy quantity. It's measured in joules. H is the elevation of the object at any moment of time relative to some ground. It need not be a literal ground. It could be any ground level or elevation reference that you find is convenient. You've seen this quantity before. It's the kinetic energy of our object, 1/2 mv squared. So we will be speaking of an object whose elevation is changing, either increasing or decreasing. At the same time, its speed will be changing. The sum of those two kinds of energies we can symbolize this way. Later, the total energy, the sum of the two is K plus U. Earlier, the total energy is the sum of the initial kinetic energy and initial gravitational potential energy. The long form of this, what we can now call the conservation of energy equation, is shown here, 1/2 mv squared for K, and you see the other correspondences. This is the long form of what we call the law of conservation of total energy, the total being the sum of the two kinds of energies this object has. The sum is the kinetic energy plus gravitational potential energy later, equaling the sum at some earlier time. The shortest form of the law of conservation of energy is shown here, where E represents the total energy. It's the sum of the two kinds of energies later, unsubscripted, and E naught is the sum of the two kinds of energies earlier, subscripted 0. And so we have E equals E naught as a statement of the law of conservation of energy. We say it's a conservation law because the total energy is conserved. That means it's constant as time goes by. Now, a situation may arise in which there are forces other than the pull of gravity that influence the motion of our object. Such forces might be, for example, friction or air resistance. Such forces, should they exist, will eat away at the energy you once had, and you'll have less energy, the sum of kinetic and potential, than you had earlier. We balance the energy equation this way. The later energy you'll have, E, will equal what you had before, plus this work quantity, which is the work done by friction or air resistance. Forces that give rise to those resistances act in opposition or oppose or are directed oppositely to the direction of motion. As a consequence of the work equals force distance cosine theta, cosine theta will be -1 because theta will be 180 degrees. And so my message to you is this: W subscript NC, symbolizing the non-conservative work, will be some negative number that we're adding here. All right, enough about that. Let's now talk about the second kind of potential energy, the only other kind of potential energy that you'll ever know about in this course, called the spring potential energy. Springs have a property called spring constant, symbolized as K. K is measured in newtons per meter. It represents the number of newtons of force that are required to stretch or compress your spring by 1 meter. when a spring is compressed or stretched, it possesses a stored energy. It's a potential energy. It's called the spring potential energy. And without proving it so, I declare that the potential energy associated with springs, the so-called spring potential energy, is found using this equation, 1/2 kx squared. Now there will be some cases in which there's no spring involved in your problem. In such a case, you'll only have the earth, which allows there to be an elevation and therefore a gravitational potential energy, plus of course kinetic energy. So we may be talking about an object rising or falling straight up and down, or an object that's rising and falling as it's traveling in one direction or the other, to the right or to the left. Thus it has elevation change and speed change, but the total energy in that case is conserved. Now, if you also have a spring present while the elevation is changing, there may be a spring that's part of your system that is being compressed or expanded or stretched. In such a case, there will be that third kind of energy to go along with the kinetic energy of the object. It's gravitational potential energy. Now it's spring potential energy, 1/2 kx squared. So I take the equation in the box that I showed you before and add to each side the spring potential energy term, unsubscripted here. Let's take away that subscript, unsubscripted there, and then we have subscripted terms over here. This is the most general equation you can have if there are no non-conservative forces such as friction or air resistance. And you'll always be told whether friction and air resistance matters. The two most important equations then are these two in the boxes. And this is of some importance, but not as important as this one. This is all you need to know to work problems and understand the content in Chapter 6.2. I hope you'll find it helpful.